Assalamualaikum and very good evening to all friends. Okay. My name is Amin Bin Suhaimi and I would like to give a lecture about the second law of thermodynamics. Okay. With this second law of thermodynamics, we can know about the second law of thermodynamics. Then we will know about heat engine, the thermal efficiency, the Kelvin-Planck statement, the Clausius statement, perpetual motion machine, and the Carnot cycle. Okay. Before we learn second law of thermodynamics, we should already learn about first law of thermodynamics. The question is why. This is because a process cannot occur unless it satisfies both of the first and second law of thermodynamics. Alright. The use of second law of thermodynamics is not limited to identifying the direction of process. It is also show that energy has quality and as well as quantity. So for the introduction, in the preceding lecture, we applied the first law of thermodynamics or the conservation energy principle to the process involving closed system. Energy is a conserved property and no process is known to have taken place in violation of the first law of thermodynamics. Therefore, it is reasonable to conclude that the process must satisfy the first law to occur. However, as explained below, satisfying the first law alone does not ensure that the process will actually take place. It is common experience that a cup of hot coffee left in a cooler room eventually cool off. This is a picture of a hot coffee and the cold coffee. Cold and hot coffee. This process satisfies the first law of thermodynamics since the amount of energy lost by the coffee is equal to the amount gained by the surrounding air. Now let us consider the reverse process, the hot coffee getting even hotter in a cooler room as a result of heat transfer from room air. Well, we all know that this process never takes place. Yet, doing so would not violate the first law as long as the amount of energy lost by the air is equal to the amount gained by the coffee. It is clear from the above that process proceeds in a certain direction and not in the reverse direction. The first law places no restriction on the direction of a process, but satisfying the first law does not ensure that the process will actually occur. This inadequacy of the first law to identify whether a process can take place is remedied by introducing another general principle, the second law of thermodynamics. We show later in part 3 that the reverse process discussed about violate the second law of thermodynamics. This violation is easily detected with the help of a property called entropy, defined in the next part. A process will not occur unless it satisfies the first law and the second law of thermodynamics. The second law of thermodynamics consists with two principles, which is Clausius and the Kelvin-Planck principle, which is the principle of Clausius states that it is impossible to devise an engine which, working in a cycle, shall produce no effect other than the transfer of heat from a colder to a hotter body. A good example of this principle is the operation of refrigerator. The principle of Planck state that it is impossible to construct an engine which, working in a complete cycle, will produce no effect other than raising of a weight and the cooling of a heat reservoir. The Kelvin-Planck principle may be obtained by combining the principle of Kelvin and of Planck into one equivalent statement as the Kelvin-Planck statement of the second law. It states no process is possible whose sole result in the absorption of heat from a reservoir and the conversion of this heat into work. Okay, the second law of thermodynamics is also used in determining the theoretical limit for the performance of commonly used engineering systems, such as heat engine and refrigerator, as well as predicting the degree of completion of chemical reaction. So the second law is not a deduction from the first law, but a separate law of nature, referring to an aspect of nature different from that contemplated by the first law. The first law denied the possibility of creating or destroying energy, whereas the second law denies the possibility of utilizing energy in a particular way. The continuous operation of a machine that creates its own energy and thus violate the first law is called perpetual motion of the first kind, a cyclic device which will continuously absorb heat from a single reservoir and convert that heat completely to a mechanical work is called a perpetual motion machine of the second kind. Such a machine would not violate the first law, which is the principle of conservation of energy, since it would not create energy, but economically it would be just as valuable as if it did so. Hence, the second law is sometimes stated as follows: a perpetual motion machine of the second kind is impossible. Okay, so we move to the thermal energy reservoir. Okay, in the development of the second law of thermodynamics, it is very convenient to have a hypothetically body with a relative large thermal energy capacity, which is mass x specific heat that can supply or absorb finite amount of heat without undergoing any change in temperature. Such a body is called a thermal energy reservoir or just a reservoir. In practice, large body of water such as ocean, lake, river, as well as the atmospheric air can be modeled accurately as thermal energy reservoir because of their large thermal energy storage capability or thermal masses. A body does not actually have to be very large to be considered a reservoir. Any physical body whose thermal energy capacity is large relative to the amount of energy it supplies or absorbed can be modeled as one. The air in a room temperature, for example, can be treated as a reservoir in the analysis of the heat dissipation from a TV set in the room, since the amount of heat transfer from the TV set to the room air is not large enough to have a noticeable effect on the room air temperature. So, a reservoir that supplies energy in the form of heat is called a source, and one that absorbs energy in the form of heat is called a sink. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat. Okay, we move to the heat engine. Work can easily be converted to other form of energy, but converting other form of energy to work is not that easy. The mechanical work done by a propeller placed in a bucket of water, for example, is first converted to the internal energy of the water. This energy may then leave the water as heat we know from experience that any attempt to reverse this process will fail. This is transferring heat to the water will not cause the shaft to rotate. From this and other observation, we conclude that work can be converted to heat directly and completely, but converting heat to work requires the use of some special device. These devices are called heat engine. Okay, heat engine differ considerably from one another, but all can be characterized by the following. First, they receive a heat from a high temperature source, which is solar energy, oil furnace, nuclear reactor, and many more. Secondly, they convert part of his heat to work, usually in the form of rotating shaft. Thirdly, they reject the remaining waste heat to a low temperature sink, which is the atmosphere and the river. And finally, they operate on a cycle. Heat engine and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called a working fluid. Okay. From the picture, this is the high temperature. Go for the system and go to the low temperature. This is the QH and this is the QM. Sorry, QC. And go for and produce a work. Core reservoir. This is the core reservoir. And this is hot reservoir. Okay, the formula is W is equal to QH minus QC, which is the efficiency is W over the QH is equal to the QH minus QC over QH. Okay. The term heat engine is often used in a broader sense to include work producing devices that do not operate in thermodynamic cycle engine that involve internal combustion, such as gas turbine and car engine fall into this category. This device operate in a mechanical cycle but not in thermodynamic cycle, since the working fluid, the combustion gases, does not undergo a complete cycle. Instead of being cooled to the initial temperature, the exhaust gases are purged and replaced by fresh air and fuel mixture at the end of the cycle. The work producing device that best fit into the definition of a heat engine is a steam power plant, which is an external combustion engine. That is, the combustion process takes place outside the engine, and the thermal energy released during this process is transferred to the steam as heat. The schematic of a basic steam power plant is shown like this. This is the pump, and this is the condenser. This is the pump. Go to the turbine. And this is the boiler, which is the work in is equal to to the work out, whereas the Q in, and this is the Q out. Alright. The various quantity shown on this figure as a follow. Q in, this is Q in, amount of heat supplied to steam in a boiler from a high temperature sources. Q out, amount of heat rejected from a steam in the condenser to a low temperature sink, which is the atmospheric in river. Work out, the amount of work delivered by steam as it expands its turbine. Work in is the amount of work required to compress water to boiler pressure. Above the quantity are in and out, and they are all positive. The net work output of this power plant is simply the difference between the total work output of the plant and the total work input, which is the formula W net is equal to W out minus W in. So the net work can also be determined from the heat transfer data alone. For a closed system undergoing a cycle, the change in internal energy delta U is 0, and therefore the net work output of the system is equal to the net heat transfer to the system, which is work net out is equal to Q in minus Q out. Okay, this is all about what I will talk before. So we move to the next objective, which is thermal efficiency. In this, Q out represent the magnitude of the energy wasted in order to complete the cycle, but Q out is never 0. Thus, the net work output of a heat engine is always less than the amount of heat input. That is only part of the heat transfer to the heat engine is converted to work. The fraction of the heat input that is converted to the net work output is a measure of performance of a heat engine and is called a thermal efficiency. Performance or efficiency in general can be expressed in terms of the desired output and the required input, as performance is equal to desired output over the required input. Or we can state that the efficiency is equal to W net out over the Q, which is Q in. Or we can state that the efficiency is equal to W net out over the Q out. Sorry, I picked the wrong formula. Okay. The efficiency, we can state that 1 minus Q out over Q in. Okay, cyclic device such as heat engine, refrigerator, and heat pump operate between the high temperature medium or reservoir at temperature TH and a low temperature medium or reservoir at temperature TL. To bring uniformity to the treatment of heat engine, refrigerator, and heat pump, we define the following two quantities, which is QH and QL. This particularity, which is QH is the magnitude of heat transfer between the cyclic device and high temperature medium at the temperature TH. QL is the magnitude of heat transfer between cyclic device and low temperature between medium at temperature TL. Note that QL and QH are defined as a magnitude and therefore are positive quantity. The direction of QH and QL is easily determined by inspection, and we do not need to be concerned about their sign. Then the network output and the thermal efficiency relation for any heat engine can also be expressed as W net out is equal to the QH minus QL, or the efficiency, we can state that W net out over the QH. Then the efficiency, we can also express it 1 minus QL over QH. Okay. The thermal efficiency of a heat engine is always less than unity since both QL and QH are defined as positive quantity. The thermal efficiency of work producing devices are amazingly low. Ordinary spark ignition automobile engine have a thermal efficiency of about 20%. That is, an automobile engine converts at an average about 20% of the chemical energy of the gasoline to mechanical work. This number is about 30% for diesel engine and large gas turbine plant and 40% for large steam power plant. Thus, even with the most efficient heat engine available today, more than one-half of the energy supply end up in the river, lake, or the atmosphere, or waste, or unusable energy. Okay, I think this is the last part of our lecture, which is refrigerator and heat pumps. We all know from experience that heat flow in the direction of decreasing temperature, in example from high temperature medium to low temperature 1. This heat transfer process occurs in nature without requiring any device. The reverse process, however, cannot occur by itself. The transfer of heat from a low temperature medium to high temperature 1 requires special device called refrigerators. Refrigerators, like heat engine, are cyclic devices. The working fluid used in the refrigeration cycle is called a refrigerant. The most frequently used refrigeration cycle is the vapor compression refrigeration cycle, which is involved for main component: a compressor, a condenser, an expansion valve, and an evaporator, like my picture. Okay, this is a picture. This is the expansion valve. Okay, can you see that? This is the evaporator. And this is the condenser. And this is the compressor. Okay. The refrigerant enters the compressor as a vapor and is compressed to a condenser pressure. It leaves the compressor at a relatively high temperature and cool down and condense as it flows through the coil of the condenser by rejecting heat to the surrounding medium. It then enters a capillary tube where its pressure and temperature drop drastically due to the throttling effect. the low temperature refrigerant then enters the evaporator, where it evaporates by absorbing heat from the refrigerated space. The cycle is complete as a refrigerant leaves the evaporator and re-enters the compressor. In a household refrigerator, the freezer compartment where heat is picked up by the refrigerant serves as the evaporator, and the coil behind the refrigerator where heat is dissipated to the kitchen air as the condenser. So for the heat pump, another device that transfers heat from a low temperature medium to a high temperature medium is the heat pump. Refrigerator and heat pump operate one on the same cycle but differ in their objective. The objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. Discharging this heat to a high temperature medium is merely necessary part of the operation, not the purpose. The objective of a heat pump, however, is to maintain a heat space at a high temperature. This is accomplished by absorbing heat from a low temperature sources, such as well water or cool outside air in the winter, and supplying this heat to the high temperature medium such as a house. An ordinary refrigerator that is placed in the window of a house with its door open to cool outside air in winter will function as a heat pump, since it will try to cool the outside by absorbing heat from it and rejecting this heat into the house through the coil behind it. The measure of performance of a heat pump is also expressed in terms of the coefficient of performance, which is COP-HP, defined as COP-HP is equal to the QH over QH minus QL. And other than that, we can express them COP-HP is equal to COP-R plus 1. The relation implies that the coefficient of performance of a heat pump is always greater than unity, since COP-R is a positive quantity, that each heat pump will function at worst as a resistant heater, supplying as much energy to the house as it consumes. In reality, however, part of QH is lost to the outside air through piping and other devices, and COP-HP may drop below unity when the outside air temperature is too low. When this happens, the system usually switches to a resistant heating mode. Most heat pumps in operation today have seasonally arranged COP of 2 to 3. So, this is the picture of the heat pump. Which is, this is the high temperature, and this is the low temperature, and this is the QH, and this is the QC, and this is work. This is an engine. So the formula, we can state that QH is equal to the QC plus W, or COP is QC over W. That we can state that is equal to QC over the QH minus the QC. then COP is equal to TC TH minus TC. Okay, so I think that's all my lecture about second law of thermodynamic. So we continue by next lecture. Thank you.